Hello everyone and welcome. In this video, we are talking about the Koenigsegg Gemera and its incredible engine. This is the world's most powerful three-cylinder engine that is also road emissions compliant. Now, the Gemera is a pretty complex vehicle, so I want to start with a high-level overview of the powertrain. Hold on a second, did you just say Gemera, like a gumoran? Look, you're going to have something to talk about in the comments. At the back of the vehicle are two beefy electric motors. They're each rated for 500 horsepower and 1000 Newton-meters of torque, and they each have a single-speed gearbox before sending power to the rear wheels independently. Sandwiched between the motors is the tiny friendly giant, or TFG, our lovely three-cylinder engine, which is placed longitudinally. This potent engine is good for 600 horsepower and 600 Newton-meters of torque. Mounted to the end of its crankshaft is another electric motor, good for an additional 400 horsepower and 500 Newton-meters of torque. If you've been adding all of that up, you're at 2000 horsepower, though the actual output is about 1700 horsepower as the battery has limits to how much power it can supply, and motors and engines make peak power at different times. Here's a plot of what those horsepower and torque curves look like. If you were to add up the three motors' horsepower, you'd get 1400 horsepower, but due to battery limitations, peak combined will be 1100 horsepower from the motors and then 600 from the engine. The engine and third motor actually send power to the front wheels exclusively, so this is Koenigsegg's first all-wheel drive model. Power is sent through a carbon fiber torque tube, then passes through a torque converter, and then through a simple ring and pinion to split power between the front wheels. On each side of the ring and pinion are wet multiplate clutches, so either front axle can be completely locked up or detached, allowing for torque vectoring. With independent rear motors, the rear also has torque vectoring, and each motor has a wet clutch to detach completely, meaning for highway cruising it can operate as front-wheel drive only for optimal efficiency. Powering all of the electric motors is a 16.6 kilowatt-hour, 800-volt battery pack. The pack is good for 50 kilometers or about 31 miles of electric-only range and can be charged using the engine, through regenerative braking, or by plugging the car in. Total combined range is 1000 kilometers, or about 620 miles. Now that's not nearly all of it, so we're going to get more into the overall layout later on in the video, but for now let's focus on this incredibly impressive three-cylinder engine. Now let's talk specs. This is a 2-liter inline three-cylinder engine. So the engine isn't very big and there aren't many cylinders. However, with a bore of 95 mm and a stroke of 93.5 mm, the cylinders themselves are actually quite large. In fact, if you compare it to Koenigsegg's 5-liter V8, these cylinders are actually larger. So how does this thing make so much power, 600 horsepower and 600 Newton-meters? Well, some engines make a lot of power by revving very high, some make it through a lot of boost. This is doing both. It has 2 bar, 29 psi of boost pressure and it revs to 8,500 rpm. You can kind of think of it like a Honda S2000 engine, which was naturally aspirated, and tripling the amount of air that goes inside of that engine. So you can make 600 horsepower and 600 Newton-meters of torque, 300 horsepower per liter, which Koenigsegg says is 2.5 times more than the next highest rated three-cylinder engine. This is the most powerful road-going 2-liter engine, and it only weighs 70 kilograms. One of the other interesting things when looking at these specifications is that it has a stroke of 93.5 mm paired with a very high 8,500 rpm redline. Combined, this is a bit unusual because that means the pistons are moving extremely quickly. We can calculate the average piston speed by taking 2, multiplying it by our stroke length, multiplying that by our RPM, and dividing by 60. If you do that for this tiny friendly giant engine, what you get is 26.5 meters per second. That may not mean much, but if we compare it to the Honda S2000, which revved all the way to 9,000 RPM with a stroke of 84 mm, it has an average piston speed of 25.2. So this is faster moving pistons than the Honda S2000's F20C engine. Versus an F1 engine, today's F1 engines are 1.6-liter V6s that rev up to 15,000 RPM with a stroke of 53 mm. Multiply this out and we get an average piston speed of 26.5 meters per second. So this thing has pistons that move as fast as F1 engines. It's got cylinders larger than Koenigsegg's V8 cylinders and 29 psi of boost. Another cool thing about this engine is that it uses Koenigsegg's free valve technology. I already have a video explaining how free valve works if you'd like to check that out. In this video, we're focusing on what are the advantages of incorporating free valve onto this engine. A traditional engine uses a camshaft to open and close the valves, and there's only one point where this cam lobe is at its peak lift, meaning peak valve lift. Koenigsegg's free valve doesn't have any camshafts. Instead, each individual valve has an actuator so you can open it completely, let it sit, and then return it using pneumatic actuators. If you look at a plot of time versus valve lift on a traditional engine, you'll see the valve lift follows the camshaft profile. However, with Koenigsegg's free valve, you pop straight up to maximum lift and then come right back down. That means you can have more airflow coming into the engine and make more power, with less restriction for that air to come in. You can also choose between all these different methods of how you want to vary timing, lift, and duration. With a traditional engine, you can vary valve timing, changing exhaust and intake overlap. The same thing applies here, but with free valve, you can also vary valve lift. Some engines only choose between two profiles, others have infinitely variable systems like BMW or Nissan. But with BMW or Nissan, when they change valve lift, they are not independently changing it, so they're also changing valve duration. Koenigsegg's system can keep duration the same while altering lift. Finally, with variable valve duration, Hyundai's engine can vary duration independently, but Koenigsegg's can independently vary both duration and lift. This is the first engine with fully variable valve timing, fully variable valve lift, and fully variable valve duration. You can choose any combination at any RPM, load, or target, whether it's efficiency, power, or emissions. You can optimize all three and choose the best setup. There are more advantages. You can choose to open only one intake valve to create swirl or tumble, or open both for better airflow. You can implement cylinder deactivation easily because you just don't open the valves. You don't need a throttle, you can use valve lift to throttle the engine, improving efficiency. Of course, there are drawbacks, cost and complexity. This is an extremely expensive car, so don't look at this and think no other manufacturer knows what they're doing. Koenigsegg can get 600 horsepower out of a 2-liter engine because the car costs over $1 million. Cost comes with these advanced features. From an energy standpoint, it's also fairly intense because it's electronic, hydraulic, and pneumatic. You have an onboard air compressor to power valve operation. The traditional spring returns the valve, but air pressure sets it down to its lift. Partially possible because of free valve, this is actually a twin-turbocharged engine. You might be wondering, wait, it has 3 cylinders and 2 turbochargers. How do you split those cylinders between the turbos? Here's the layout. You can see the 3 cylinders, each with 2 exhaust valves. Each exhaust valve routes to a different turbocharger. Air comes in through the compressor side, travels through the air-to-water intercooler, and enters the engine. At low RPM, only one exhaust valve is open, so exhaust goes out one side and spools one turbocharger. Then as RPM increases, both exhaust valves open, spooling both turbochargers and making peak power. At low RPM, this single turbo setup allows peak spool at 1,700 RPM, and from 2,000 to 7,000 RPM, both are active, producing 600 Nm of torque. It's a very clever strategy combining turbocharging and free valve control. Let's go back to the layout. Like the Koenigsegg Regera, there are not multiple gears here, just a single gear ratio. The tiny friendly giant engine at the back, coupled with its motor, sends torque to the front through a 2.69:1 ratio, while the 2 rear electric motors each have their own 3.325:1 gear reduction. Add up the wheel torque, in the front, 600 Nm plus 500 Nm, multiplied by 2.69 gives 2,960 Nm. In the rear, 2 motors each with 1,000 Nm multiplied by 3.325 gives 6,650. Combined, that's 9,610 Newton meters. Koenigsegg says actual wheel torque peaks at 11,000 Newton meters thanks to hydraulic coupling. This coupling can multiply torque up to twice at low speeds, below 3,000 rpm, before locking up for efficiency. These gear ratios are fairly low compared to traditional vehicles, maybe a third or a fourth, but that allows crazy high wheel torque and still a top speed of 400 km per hour, 250 miles per hour. I calculated the gearing and wheel size. It could theoretically reach 260 miles per hour ignoring tire deformation, but with real-world conditions, 250 miles per hour is accurate. It's geared for insane acceleration, 0 to 100 km per hour in 1.9 seconds. If true, that's an average acceleration of 1.49 g, something not yet seen in a production car. It'll be interesting to see real-world results. This powertrain delivers stunning acceleration up to 250 miles per hour, making it both a technical and engineering masterpiece. Quite a cool vehicle, and quite a cool engine that has gone into it, of course, all at a very expensive price, but a very neat thing nonetheless. Thank you all so much for watching, and if you have any questions or comments, of course feel free to leave them below.